Okay, good afternoon. My pleasure to introduce Ehud De Shalit from Hebrew University, who will give a second lecture on moduli of divisible groups.
Okay, so thank you. So yesterday we reviewed the theory of p-divisible groups and formal groups, and then we constructed the Lubin-Tate moduli space, which will be our main example. Let me go quickly over the last few slides from last time. So K was an algebraically closed field of characteristic P, little k. H0 was a fixed model of the unique one-dimensional formal group, p-divisible formal group of height h above k. W the Witt vectors, and Ck the category of local complete Noetherian rings with residue field k. And for any R in this category Ck, we consider all the couples G iota, where G is, so to speak, a deformation of H0 to R. So it's a one-dimensional p-divisible group of height h again, it will necessarily be, over R, whose reduction is isomorphic to H0, but I want to equip it with an iota, which is such an isomorphism. And the theorem of Lubin and Tate from 1966 says that this functor that sends such a ring to the set of such pairs is representable basically by the, by a formal scheme, but you should think of it, and when we get to adic spaces, you'll see that this is the associated adic space. You should think of it as the H-1 unit polydisk, open unit polydisk. You see, if you plug in for U1 up to UH-1, numbers in a ring are equipped with a complete valuation, or they are less than 1, then any such power series will converge. And we briefly went over the proof, which was based on this idea of Hazewinkel and Lazard of universal one-dimensional formal group law. So all that I want you to remember from this is that these coordinates, U1 up to UH-1, are obtained by specializing the first H-1 coordinates in this universal formal group law. And the rest, the H1 is specialized to 1 and the rest to 0. And as I said, you can have a more general theory where you replace formal groups by formal A modules, where A is maybe a ramified complete discrete valuation ring that always acts on your group as endomorphisms. So in our case, A is simply ZP, and you can also do it when this A has characteristic P, and then you get the theory of Drinfeld modules. And when all the UIs are specialized to 0, you get what's called the canonical lifting, and in this case, you get the Lubin-Tate formal group of height h over the Witt vectors. If you use this in conjunction with the previous remark, you can do it over ramified basis, and then you can get all the other Lubin-Tate formal groups as canonical liftings. Fine. So as we do with modular curves, we want to enrich or enhance the moduli problem by allowing level structure. And as you probably know, level structure becomes problematic, even in modular curves, when you consider P power level structure over rings in which P is non-invertible. And the right thing to do it, to give good moduli problems, was discovered by Drinfeld. So a Drinfeld level n structure, or rather a level P to the n maybe, structure on a couple G iota is a homomorphism of finite flat group schemes over R, over the ring where this G iota is given, from the constant group scheme Z over P to the n Z to the power H, to the P to the n torsion of our p-divisible group. And the crucial thing is that if you sum the images, so the image of every point X is a section, right? The image is a section, and I say as Cartier divisors, well, you may argue that this is not anything of it's not one-dimensional. It's zero-dimensional, maybe GP to the n. But what we mean is that if we embed it in the formal group, which is one-dimensional, then really this equality holds as Cartier divisors. Or really in down-to-earth terms, remember this G is given as the p-divisible group associated with some formal group. It's a one-dimensional formal group, so it has one parameter x, fix such a parameter. And then in terms of that parameter, the endomorphism of multiplication by p to the n is given by some power series. But on the other hand, you can consider the polynomial of degree p to the nh, which is the product of x minus alpha n of x. Alpha n of x is just a point, so this is just a value in the maximal ideal of R. And these two should be associates. They should generate in the power series ring over R the same ideal. So as an example, if we took the multiplicative formal group, alpha n is simply a root of unity of order p to the n in R. And if you think for a moment what this condition means, it simply means that this satisfies the famous cyclotomic polynomial of index p to the n. Of course, you reduce it from z to r, whatever, or you base change it from z to r, whatever that means in R. And now you can consider the enhanced moduli problem, which I call Mn of R. Previously it was M of R, where you consider G iota as in M, and in addition a level n structure alpha n. And we immediately note that previously, remember that iota was not necessarily an isomorphism, it was a quasi-isogeny. If I want a component where it is an isomorphism, I put a 0 on the top. But otherwise there's z being the integers, copies of the same thing. Not only, previously the division algebra of invariant 1 over h over qp acted by changing the iota. It still acts, you see it. G1 acts by post-composing iota with G1, but you can also act with GLH z over p to the nz by pre-composing alpha n by the automorphism, the constant group scheme. So you get these two groups acting. And the main theorem, which is deep, I'll not go over the proof, of course, says that, as before, this is representable by the formal spectrum of a ring AN. This ring is pretty nice. It's regular, complete local ring. And of course, it maps to, or the moduli problem maps to a formal spectrum of A0. So this is a ring over A0, and it is finite and flat over A0, but not et al. That's the whole point. In the special fiber, there is a lot of really bad ramification. And yeah, I'm always talking about the connected component where the quasi-isogeny has height 0. And it is et al. In the generic fiber. And I want to say something about generic fibers of formal schemes. So in the old days, people had formal schemes, and people wanted to associate to them in some way rigid analytic space, whatever that meant. Okay, so some analytic space over which you can do p-adic analysis. And there was a procedure which was called taking the generic fiber. I said special fiber, I meant generic fiber. Generic fiber. Taking the generic fiber in the sense of Raynaud. That was the phrase. And this was a little bit cumbersome because it was really not the generic fiber of anything. Okay, so a formal scheme was just, say, if you want a sequence of schemes over z over p to the n. Okay, so there was nothing in characteristic 0. And then you want to create something in characteristic 0. Using the machinery of adic spaces that we have started seeing this week, you can make sense of it in the following way. You take the affinoid adic space SPA A0 A0. We have seen the definition. I do not want to go over it again, but you should have some idea about what this is, and then you take its generic fiber by taking the product over SPA of the Witt vector with itself with SPA of W1 over PW. So this simply means, as a set of valuations, looking simply at all those valuations where P doesn't get the value 0, okay? Where P is not 0. But one should be careful because it's a product of two affinoids. In itself, it's not an affinoid. This can happen in this world of SPAs, and it is rather an open polydisk. And now we can also make a formal scheme in the following way. We can take the direct limit of all these ANs, and each of it is, remember, a regular local ring, but although the ideal I, which was the maximal ideal of A0, is not maximal anymore, it's still, since the maps are finite, you can still complete with respect to the same I and not change the I as you go. And if you go all the way up and complete still with respect to the same I that comes from A0, then you get a complete and separated ring, because it's a finitely generated ideal, and the formal spectrum of this is the formal scheme structure at infinity. And again, one has to be careful technically. This is a not Noetherian ring anymore, so it's not absolutely clear that the associated SPA is adic. I hope we will come to this issue in the series of lectures about Huber spaces and adic spaces. The point to check is what is the sheafiness of the structure pre-sheaf, but this follows from the fact that we will see later that A infinity is not only an adic ring, but it's actually a perfectoid ring. And again, we take the generic fiber of this thing, and this is the analytic Lubin-Tate space at the infinite level. So to sum it up, we have added level structure, we've constructed the formal scheme all the way up, and we can take its generic fiber either in the sense of Renault and get a rigid analytic space as in the old days, or as we did here in the sense of Huber. And what does all this mean where H is 1? So where H is 1, remember, there were no variables. In general, there is H minus 1 variables, so there's no variables. And the formal group of height 1 is the multiplicative formal group. It's rigid. It doesn't have any deformations. But it does have level structure. And as I said before, adding a level structure is simply choosing in your ring R, over which it is defined, a solution of the cyclotomic polynomial. So what is the ring that represents this? This is very easy. It's over the Witt vectors, it's Wx over phi b to the n, right? Homomorphism from this to R is such an alpha n of 1. But this is simply the ring of integers of the field obtained from adjoining zeta p to the n primitive root of unity to the completion of the maximum ramified extension of QP. And by the Kronecker-Weber theorem, when you go all the way up and you complete, you simply get the completion of your maximal abelian extension of QP. So as we have seen, well, we've seen it with QP adjoin all p to the n roots of unity, all the more so it's true in this case. This is a perfectoid field, right? This was one of the basic examples that Kiran gave. And its tilt, if you do not go all the way up, the unramified tower was just power series in t to the 1 over p to the n for all n completed. If you go up the unramified tower, it's the same, but the field of scalars changes from Fp to Fp bar. So this is the first instance of a principle where the Lubin-Tate tower at the infinite level is a perfectoid space, which is one of the main achievements of this theory of perfectoids in the setup of moduli spaces of p-divisible groups. Yeah, and we can also make very explicit the actions both of OD star and of ZP star, GL1 ZP on the tower. They're both given by the cyclotomic character and the inverse cyclotomic character. So now we come to the second lecture, a little bit later, but that's fine. And today's talk will be mostly devoted to crystalline Dieudonné theory, and the word crystals will figure out prominently. But there will be two different crystalline constructions. Yeah. Questions, actually. Sorry for not letting you ask, but that's a good time.
Can you go back one slide?
Yeah. W is the Witt vectors all the way up. I always start with little k being FP bar. No, not stupid. Okay, more questions. That's a good time. Sorry for not giving time for questions. Yeah. Okay, we'll come back to the Lubin-Tate tower soon today. So there will be two type of crystalline constructions. One will be the universal covering of a p-divisible group, and the other one will be the crystalline Dieudonné module or the crystalline Dieudonné theory, and I will have a little tour of Grothendieck massing theory, which is by now classical, but I think that is not very accessible if you just try to read the books by Messing. Good, so let's start with universal covering of G. So we start with an adic ring over ZP. So remember, this is a complete and separated ring in some I-adic topology, where I is not specified. But assuming that it's over ZP means that you can throw in P into I. Okay, that I can contain P. P is topologically nilpotent, and then G, a p-divisible group over that R. And remember that we redefined the notion of the S points of G over any R algebra S to be the inverse limit of G of S over IS to the n, so that it coincides with the S points of the formal group in case that G is formal connected. And here's the definition, simply as a presheaf, simply as a functor on rings. So for any ring S, adic ring over R, we let G tilde of S be the inverse limit with respect to multiplication by P of G of S. Okay, so it's simply all the sequences, x0, x1, x2, etc., so that xi is an S point of G, and P maps xi plus 1 to xi. Now, this is, of course, a presheaf of groups, but it's also of QP vector spaces. P acts by shifting to the left, right? If you multiply this by, shifting to the right. If you multiply this by P, instead of x1, you get px1, which is x0. Instead of x2, you get x1, and so on. And 1 over P by shifting to the left. So this becomes a QP vector space. And as easily computable examples, if you start with a constant p-divisible group QP over ZP, its universal cover is QP. If you start with mu p infinity, let's see what this is. We already worked out the S points, say, in OC. So they were 1 plus the maximal ideal of C. Okay, not just the p power roots of unity there. Okay, because of this new definition, there were really the whole unit disk around 1. And when you take its inverse limit with respect to raising to power p, you get, as we learned from Kedlia's talks, the same unit disk, but in the tilt of C, 1 plus the maximal ideal of the tilt of C. Now, because these are QP vector spaces, the universal coverings are isomorphic even if the p-divisible groups are only isogenous. Definitely they're isomorphic if the p-divisible groups are isomorphic, but you see an isogeny is a homomorphism such that you can follow it by another homomorphism so that the composition is some multiplication by power of p, and multiplication by power of p is an isomorphism on QP vector spaces. So this will be important. And now comes a rather easy lemma, but which is crucial for all that we will be doing. And this is that what I call the crystalline, without talking about crystals in this setup, simply I'll call it the crystalline nature of G tilde. And this is that if you have a closed, topologically nilpotent ideal I, then G tilde doesn't change at all. G tilde of S and G tilde of the reduction is the same group. So there's an obvious map, which is the reduction mod I, but this map is one-to-one. And maybe it's time here to add a little thing on the blackboard, because this thing was asked, and it's the same principle, this thing was asked in the talks defining theta and sharp. So remember that Kiran defined theta, maybe he had a bar here. This was the summation of xn bar sharp p to the n. And there was a question, what is x sharp? So x sharp in general, or alpha sharp, so alpha, remember, was in this inverse limit where AI was in OK over P, or in our case in OC over P. And alpha sharp will simply be the limit. So Kiran said it, but I think he didn't put it on the blackboard, so I want to put it on the blackboard because it will be exactly the same principle as here, the limit of A I tilde to the p to the I. So you lift AI to OK in any way that you wish, and you take this limit, and this limit exists. And the reason that this limit exists is the same reason behind this proof. Let me give it in the context of this proof. You start with a point y in the universal covering over the reduction S over I, and you lift the yi, so the yi's are p-compatible, but you lift them arbitrarily. This, of course, you can do because this is a formally smooth group, or if you want, just think of the formal group. It has d variables. You just lift each of the variables as you wish. And then you let xi be this limit. So if we were only concerned with x0, it will be exactly what we did there, but now we're concerned with all the coordinates. So xi is the limit of p to the j applied to zi plus j. And why does this limit exist? Because think of the formal group point of view, where you have many variables, and multiplication by p is given again by d power series in d variables with coefficients. But one thing is known, and this is that all the coefficients that are not divisible by p have exponents which are powers of p. Now, applying such power series has the advantage of improving congruences. Okay, if you have 2 points that are defined by 2 sets of parameters, x1 up to xd, and they are congruent modulo p, or modulo p to the 10, and you apply such power series, the result will be congruent mod p to the 11. Because, yeah, that's well known. And this immediately shows that this sequence that we define there is a Cauchy sequence, and it also shows that it's the only possible lift. So the lift exists and it is unique. So this very simple principle, which is behind the definition of the sharp map, proves this crystalline nature. And therefore, we will simply adopt the following convention that if T to S is any nilpotent or pre-nilpotent thickening, simply meaning it's a surjective map of rings whose kernel is nilpotent or topologically nilpotent, then we know by Lazar that we can always lift G to T, and there will be many lifts, but the universal coverings of them all will give the same result on T because it will be the original universal cover of G on S. So we'll simply write it by abuse of language, abuse of notation, as G tilde of T, although G tilde is not defined over T, only over S, and to make sense of it, you need to take some lift, but any lift will do, and the resulting groups will all be canonically the same. So this is the first appearance of the notion of crystal. So we define this universal covering as a pre-sheaf, and the first question that might come to your mind is whether it is representable. And first result is that it is representable, in fact, by a non-Noetherian ring, but representable in case that R, or a ground ring, is a perfect FP algebra. And G is formal. And then G was represented, of course, by, as a scheme, forget about the ring, about the group structure, by R with power series in D variables, and its universal covering will be representable by, again, as a scheme. I do not tell you what the group structure here is, but as a scheme, by a formal scheme, by power series with variables x1 to the 1 over p to the n up to xd to the 1 over p to the n for all n, and completed in the x1 up to xd adic topology. Okay, so that's a shorthand notation. And the key idea here is rather simple. You can find the full proof in the paper by Scholze and Weinstein. The idea is to replace the inverse limit over P by inverse limit over Frobenius. And using the relation between Frobenius Verschiebung P, F times V equals P, you see that in this case you get an isomorphic group. Now it's obvious that when you do the inverse limit over Frobenius in characteristic P, that's what you get because you just extract P roots each time. But there's one technical issue that while multiplication by P takes you from G to G, multiplication by F, or applying Frobenius, doesn't take you from G to G, it takes you from G to GP, but if you want to go backwards, you have to sort of take GB minus 1, GP minus 2, and so on. So you have to apply to the coefficients of P the inverses of Frobenii, and for that you have R to be perfect. So that's where the perfectness of R comes in. Now, it's important to have, we will be focusing later on P-divisible groups over OC. C is CP as usual. Some of the main results of Scholze and Weinstein that I want to survey are classification of P-divisible formal groups over OC. And it will be important to have such a representability result not over perfect FP algebra, but over OC. And you've already seen that OC is in characteristic 0, but in a sense, it's almost perfect. It's perfectoid, okay? And this perfectoidness allows you to prove a similar representability result, but it relies on a very deep theorem of Farg, Scholze, and Weinstein, and which is called the isotriviality theorem. And actually, if anybody knows of a simple proof of this, I have the feeling that there should be for this theorem a simpler proof than there is today in the literature. But if anybody knows, I'll be very much interested. So it looks officially a little bit like the theorem that we talked about yesterday, superficially, a little bit like the theorem that we mentioned yesterday of rigidity of quasi-isogenies, in the sense that, what does it say? It says that if you mod out by P, okay, so OC over P, of course, is not a field. It has lots and lots of nilpotents. Okay, so if you mod out by P, then the reduction of G modulo P, which is the left-hand side, is quasi-isogenous to the isotrivial p-divisible group, which is the reduction of G all the way modulo the maximal ideal, but then base changed from Fp bar to OC over P. So you understand the difference between the two sides of this quasi-isogeny. The right side is isotrivial, and up to the notion of being quasi-isogenous, the reduction of G mod P is also isotrivial. And this is not a formal consequence of rigidity, because you cannot apply, as I said before, rigidity of quasi-isogenies to reduction by MC. You cannot lift from OC mod MC to OC over P, because MC is not topologically nilpotent. You can lift from OC over square root of P to OC over P. You can lift from OC over the 100th root of P to OC over P, but not from OC over MC. And as a corollary, really formal corollary of this theorem, you get the representability of G tilde over OC. I will leave out the proof. It's 2 lines, and it's really formal consequence of what we know so far. The crystalline nature of G tilde and this isotriviality theorem. You switch back and forth between the group over OC, its reduction, and then you compare it with the isotrivial group. Now, you may ask, my first statement in the first lecture was that we want to abandon the Tate module approach because the Tate module is too small, it's not good for deformation problems. But now the Tate module comes back in the back door because the Tate module is obviously a subfunctor, a subgroup functor of the universal cover. What is the Tate module? Is the inverse limit, with respect to multiplication by P, just of the P to the n torsion points of G. Remember? Not of the whole G, but just to the P to the n torsion points. So in other words, it's all those elements that we had before, x0, x1, etc., 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 but now with the provision that x0 is 0. x1 is of order P, x2 of order P squared, and so on. And since G tilde is a QP vector space, not only the ZP Tate module, but the QP Tate module, the rational Tate module VP, embeds in G tilde. But there is one important warning. That's a lesson that I want to carry with us all the time. While G tilde was really insensitive to nilpotent thickenings, in other words, if you had a nilpotent thickening by the crystalline nature of G tilde, the value at T did not depend on how you lifted G. The subspace that we now defined, VP G prime, very much depends on the lifting. If you try to imitate the proof that I had here, okay, at the end of the slide, it will fail because you will not be able to lift a P to the n torsion point to a P to the n torsion point. The whole formal group is formally smooth, not the P to the n torsion. So this is an important observation, and what we're aiming at now is an exact sequence that has first the inclusion of VPG in the universal covering, and then a map that will basically be a logarithm map, but I call it theta because it will be intimately connected later to the theta that we saw in previous lectures, to the Lie algebra of G, but for that we have to assume now that S is flat over ZP. So there's always this game where you define things first over rings in which P is nilpotent, then you go via inverse limits to p-adic rings which are flat over ZP, which have no torsion, and then you invert P. Only then you can invert P, so only then you can talk about logarithms, as you all know. And here's a spoiler. At the end of the series of lectures, we shall recover this naive logarithmic sequence when S is a perfectoid, or we will do it only maybe when S is OC, as the global sections of a certain exact sequence of modification of vector bundles on the Farag-Fontaine curve, which will be the main character that we will meet later on. So to define this, I have to talk a little bit about logarithms. And again, excuse me if some of you may know it all. It's very, very similar to the theory of logarithms in Lie groups or in p-adic Lie groups. So any p-adic Lie group has a logarithm from the p-adic Lie group. Sorry. From the p-adic Lie group to its Lie algebra. But we want to define it here in the context of formal groups. It can be done. The surjectivity of this logarithm map will be an issue that will be solved when S is, for example, OC, but in general, let's leave it as it is. It's not always surjective. So quickly, let's go over logarithms. So let's start with a formal p-divisible group. Its associated formal group I call script G. So it's formal spectrum of some ring A, which is power series in D variables. And the cotangent space at the origin can be identified simply with a free R module on the basis dxi. But as usual in Lie theory, you can extend any element of the cotangent space at the origin to a left invariant, or here it's commutative and invariant differential. And the invariance means that when you apply co-multiplication, you get omega times 1 plus 1 times omega. So these are the translation invariant differentials, and I identify always omega with them. And as usual in Lie theory, translation invariant differentials, even in the higher dimensional case, are closed. And when R is flat over Zp, for every such omega closed and translation invariant, there exists a logarithm. You can formally integrate it, and it's unique if you insist that the logarithm as a power series doesn't have a constant term, but the price that you have to pay, of course, is that you introduce denominators. But that's why I have the little, you are very sharp, but you see this little thing here? This is completion. You're absolutely right. I cannot just invert P. I should invert P and complete because the denominators grow. You're right. So this is the formal Poincare lemma. So what did we do? For any omega, we associated a homomorphism, a logarithm, which is homomorphism from G to the additive group. But of course, homomorphisms from omega to homomorphisms from G to GA is the same by general nonsense as homomorphisms from G to homomorphisms from omega to GA. So in this way, we get, for any element in, we get a canonical homomorphism from G to simply the Lie algebra. And the underline, I was asked about it, simply means that I view these things as vector groups. So not only for R, but as the functors that associate for any S tensor that module. And then the map theta that figured out in the previous slide is simply applying this logarithm from the group to the Lie algebra to the first coordinate, to the 0th coordinate. So you project from the inverse limit on the 0th coordinate, and you apply theta. Now think of it. When is the logarithm of something 0? If and only if this something is torsion, right? Because you can always multiply by a high enough power of p to bring it to a small neighborhood where logarithm converges and has the exponential is defined and everything is 1 to 1. So if you got there, then if the logarithm is 0, then you would rather have 0. So the thing with which you started before multiplying by the power of p is torsion. So this means that the kernel of this projection to the first, or rather 0th coordinate n log, is simply all the sequences where x0 was torsion, but this is exactly VP. TP is all the sequences where x0 is 0, VP is all the sequences where... Okay, so this proves the exactness of this naive logarithm exact sequence. And I said that if the projection to GS is surjective, then theta will be surjective too. In algebraically closed cases, this will be the case. So, yeah.
Well, first of all, log of p is 0, that's by definition.
No, that's not the Iwasawa logarithm. That's not the Iwasawa logarithm, that's the Lie group logarithm.
So it's simply a projection of the domain. So there's no radius. Like for GM, the log doesn't go all the way projected.
No, but for GM, okay, if we were in GM, this would, the GM hat would only be principal units. So there's no issue of how you define log p. For GM, it would be the usual logarithm, okay? But the normalization of log of p, as we do in Iwasawa theory, does not come into the picture.
No, forget the p, but I'm saying that over 1 plus PCP is bijective.
Absolutely, yeah.
It's defined even further, it's defined with the whole...
Okay, fine, but it defines...
But you cannot say what the kernel of the whole...
Oh, the kernel on the whole is always roots of unity, yes. Oh, absolutely.
But the explanation is not really defined the other way on the whole thing.
No, it doesn't matter. But you can, as I said, you can take anything in the unit disk in CP, say, raise it to a very high power of p to bring it very close to 1. Okay? And then apply the log. And if it's 0, then you'd rather have 1 because log is injective already there.
This argument works.
No, this argument. Yeah, and that works in general. Okay. Any more questions? This is a good point. I'm going much more slowly than I planned to, but that's okay because some of the things that I plan to do in later talks will be done by other people, as we agreed. So, any questions so far? If not, let's apply this construction of the universal covering to get a very nice and simple description of the Lubin-Tate tower at infinity. And this is actually something pretty recent and comes as a really nice surprise because anybody who is familiar with a book by Katzenmazer, for example, knows how much pain it is to understand Greenfield moduli structures, level structures or Greenfield moduli problems at finite levels. Okay, integrally. But the miracle is that thanks to this point of view of perfectoids, of doing things all the way at the infinite level, there is a very nice description of M infinity that does not factor through finite levels. So, and it's due to Weinstein. He first did it in height 2 simply because he didn't have this result of Hedayat-Zadeh from 4 years ago. But let me now explain how it is done in general. So again, R is our local complete Noetherian ring with residue field K, which is algebraically closed of characteristic P, and G iota is such a pair, and the height is H. And let us fix the canonical lifting, this Lubin-Tate group of H0 all the way over W, over the Witt vectors of FP bar. It is then unique up to isomorphism. So this is notation. Now, what Hedayat-Zadeh proved is that there exists something that behaves like a determinant in formal groups or p-divisible groups. So it proved there exists a canonical alternating multilinear map, lambda n, from gp to the n to the power h, h is the height, to mu p to the n, satisfying the obvious universal property that if you have any other alternating multilinear map from gp to the n to the h to some other group scheme whatsoever, it will factor through this map. Okay, there will be a map from up to the n to that other group scheme through which this factors. And this is an amazing result. You would think it's a very elementary result, but at least the way he proves it uses some sophisticated tools, I think, from Zing's theories of displays. And again, it's something that might be simplified in due time, but at least something that's easy to trust. In the case where h is 2, you probably know an example of this. When h is 2, this G of height 2 is simply the p-divisible group, or at least over fp bar, sorry. It is the p-divisible group of a supersingular elliptic curve, and maybe liftings of it are p-divisible groups of liftings of supersingular elliptic curves, and then this lambda n, in the case that h is 2, is the Weil pairing. But in general, it's not a bilinear pairing. It's like a determinant. It's a multilinear pairing. Now, remember that iota gave us a way to identify the universal covering of S over ms with the universal covering of G, sorry, at S over ms, with the universal covering of H at S over ms, right? It was a quasi-isogeny between G and H, so it produced an isomorphism between universal coverings when you apply it in S over ms, but the universal coverings at the level of S over ms are the same as the universal coverings of S by the crystalline nature. So having a iota at hand allows us to identify the universal coverings of G and H at S. So H is our fixed Lewin-Tate group lifting of H0, and G is an arbitrary deformation. And it is easy to see that if you compare the maps that you get from this theorem for H and for G, they should be equal up to a scaling factor, and this scaling factor I call lambda of iota. And in fact, if iota is not only a quasi-isogeny but an isomorphism, really, so if it is of height 0, then this is in ZP star. And now let's look at the universal covering of H and the universal covering of GM. H is a one-dimensional formal group, so I use X as a parameter on H and T as a parameter on GM. And in this case, what does lambda H mean explicitly? So you have to have little h copies of H, so little h copies of the variable X that I call X1 up to XH. Okay, they correspond to the H copies there. And of course, the parameter, okay, a map in this direction, like lambda, goes in the opposite direction on the adic rings that represent these formal groups. And this simply means that for each t to the 1 over p to the n, remember the universal cover of GM is represented by this formal spectrum of w t to the 1 over p to the infinity. So for each t to the 1 over p to the n, you have to give yourself just an element, delta, that I call delta to the 1 over p to the n. That's just a notation in the power series ring in h variables over r again. These variables being perfectoidized. I don't know how to make a verb from perfectoid to perfectoidize, maybe. You take all p power roots affinity. And these power series should be compatible, of course, in the sense that the pth power of delta to the 1 over p to the n plus 1 is what I call delta to the 1 over p to the n. This corresponds to the compatibility under p in the universal coverings, and should also satisfy some easy relations that reflect the additivity and alternating condition. Okay, so that's a multilinear map, so it's additive in each variable separately and alternating. So you can write down what it means. You'll have to apply inside between the x's the formal addition of the formal group H, and outside, once you get the result in your in GM, you'd have to apply the formal addition of GM. So now we can make, using this beautiful determinant, a diagram. And let's go very slowly over this diagram that is in the box. So on the bottom row, we have the H-fold product of the universal covering of our fixed H, okay? And this maps via this map lambda H, just for this fixed H, to the universal covering of GM. On the top, we have a similar thing, but now on the moduli space level. So you look at M infinity, and a point of M infinity, so I'm now explaining the top map, which is this thing, okay? So a point of M infinity over some ring R, I'm not writing down the R, is a triple G iota and a level infinity structure, alpha infinity. But the level infinity structure gives you, at each finite level n, it gives you alpha n1 up to alpha nh, which are the bases, so to speak, the Drinfeld bases, so to speak, of the p to the n torsion obtained as the images of the canonical basis of z over p to the n to the h. Okay, you have z over p to the n times z over p to the n, etc. So you have E1 up to EH, and they map to alpha N1 up to alpha NH. And you can apply to these lambda NG and get a root of unity. Okay? And you would like to map this to, remember our L, which was the OL, which was W, join all p power roots of unity. This was, so to speak, the cyclotomic extension completed on top of the Witt vectors of Fp bar. So we would like simply to map zeta p to the n to this and make a map like this, which is a map of formal schemes over W, except that to make this commute, I multiplied. I also have the iota that I have not used so far, so I multiplied by lambda iota, by this scaling factor that comes from iota. Okay, so that's the top map. Now, the top map is clearly, the way it's written, comes from limit at finite levels. You see, I wrote it, what it does at each finite level, and these maps, these determinant maps are, of course, compatible at finite levels, as the Weil pairing is in the case of h equals 2. Okay, now what is the left vertical map or the right vertical map? They are the same basically, except that the right vertical map is just in the case of GM and the left is in the case of a general situation where you do have deformation. So for GM, remember, the formal group was rigid. There was no real deformation, but there was only level structure. But on the left, that's really the whole moduli space. So you start with G iota and alpha infinity. And you simply forget the iota, and you simply project the alpha infinity. So again, you get compatible. So of course, the level structure, the Drinfeld level structure, gives you compatible sequences under multiplication by p. That are the images of the basis elements of z over p to the n to the h. And these give you simply elements of the universal covering by definition. So I've defined all these maps, and yeah, there's a little point here that I swept under the carpet, and this is, why do I have this disjoint union over z copies indexed by the integers of the same spef of OL, and this is simply because the iota can be quasi-isogeny. So if you only did height 0, you'd only have one copy there, and on the left you'd have M infinity upper 0, the connected component, so to speak. And you see, all the maps are defined and are very simple to define. And the amazing theorem is that the diagram is Cartesian. In other words, you can get M infinity as the fiber product of these two maps, these very elementary two maps. This map we have described before when we dealt with H equals 1. And this is basically this determinant map. And it is simply the fiber product. Now what this means morally is that all the depth and complication of M infinity lies in this determinant map. And this is an amazing result. It also allows you to describe the action of GLH and D star on M infinity very easily. Let's, for example, take GLH of QP. So GLH of ZP we have described before, but once you go all the way to the top, just as you do in modular curves, you actually get, right in modular curves, you get all the, or Shimura varieties, you get all the Hecke correspondences, all the GL2QP acting. So here you would get them too, and this would simply, or GLH, sorry, not GL2, modular curves is GL2, here is GLH. GLH QP would simply act by acting on the right on this. Okay, so you take a matrix and you just view this as a row vector and you act on the right. And here you have to act by the determinant of the matrix. Maybe you have to invert things to make it an action and not an anti-action, but that's the usual business. And the action of D star is by its action here on each individual H tilde. Okay, so remember that D was the quasi-endomorphisms, okay, the quasi-Homs from H naught to itself. The Homs was OD. And it acts on H tilde, but H tilde is the same as H0 tilde. So it acts on H tilde. And again, on the right column, you have to let it act through the analog of the determinant, which is the reduced norm. So I just want to emphasize again, the main point here is that this theorem is only available at the infinite limit because the vertical maps do not factor through or are not obtained as inverse limits of maps at finite levels. So you do not have, unlike the horizontal maps, a way to describe what happens at a finite level, but rather at the infinite level. And here are some corollaries. First of all, if you now take the two groups that act, but inside the product you only take the elements where the determinant of the first, which is an element in QP star, is the reduced norm of the second. So these elements will act trivially on the right lower corner, right? Because one element acts like determinant, the other one like the inverse of the reduced norm. So they will act trivially here, and they will act on these two sides. So via the fiber product, they will act on M infinity. So you get a good explicit description of everything. And also, thanks to this description that we had in the case of H equals 1, you have, and these deltas, you get a really concrete description of the ring A infinity, which is a non-Eutherian power series ring in, or perfectoid power series ring in x1 to the 1 over p to the infinity up to xh to the 1 over p to the infinity, divided by the relations delta to the 1 over p to the n minus t to the 1 over p to the n, where t was this element in OL that I have not explicitly defined before, but is in here. Okay, this element t really corresponds to a certain inverse, or not inverse, a certain limit like the one that I have there on the blackboard. Okay, so the upshot of everything, and I will stop here. I have not said anything about a crystalline net theory. This will be the topic for tomorrow. I'm going much slower than I imagined, but I think it's better this way. The Lubin-Tate tower at the infinite level, thanks to these ideas, is infinitely simpler than at finite levels. And in addition, the one bonus that you get is you look at this ring A infinity and you obviously see that it is perfectoid in appropriate sense. So we have not talked yet, it will come up in other lectures, about perfectoid spaces. And we're really interested not in this ring, but in the generic fiber, in the sense of Raynaud, or in whatever sense I gave it before. But the shape of this ring, where you really extracted, right, it's obvious that if you take this ring and you mod out by P, then OL was a perfectoid, and the variables that you added Pth roots of them. So raising the power P will be surjective, and that's the basic idea behind proving that the generic fiber, this adic space, is also a perfectoid space. So that's one of the main results of Scholz and Weinstein. So what we'll do tomorrow, we will talk about crystalline Dieudonné theory, and we will tie both crystalline constructions into one big diagram. And this one big diagram will show up later when we talk about the Fark-Fontaine curve in a completely different and more transparent way. Okay, thank you.
So there is some hot state and Gross-Hopkins period maps. So is there something, can you build it out of this, period maps?
Yeah, so we will talk about the period maps.
Okay.
Sorry?
No. So is it something to do with this diagram? This.
Yeah. Well, the Gross-Hopkins period map, which is the same as the Groningen-Messing period map, is not directly in this diagram, but it's related. I mean, we will talk about it tomorrow, hopefully, or maybe if everything is a little bit postponed, maybe on the fourth talk. Yeah. But it's definitely related. It's related to this map theta, and it's, yeah. So my aim is to present classically, so to speak. Of course, this is something recent, but classically, the theory up to the point where you have the Fark-Fontaine curve, then introduces a black box, the Fark-Fontaine curve, and I hope that Denis and Kiran will say more about the actual proofs of the black box theorems, and then deduce all kinds of deep results, rather conceptually, from the Fark-Fontaine curve picture. I don't know if I'll be able to finish it all, but we'll see. But the periods map.
Are there any questions? Okay, so let's thank Ehud again, and we'll reconvene in 15 minutes.